So we have two example here. The first example is given that an extrapolated dimension of a PWR, radius extrapolated is 67 inch, and the height extrapolation height is 144 inch. Power and 1893 megawatt thermal power, and contain a 190 fuel assemblies, and each consists of 204 uranium oxide fuel rod with a 0.42 in diameter, and also assume the assemblies are assumed uniformly distributed. So the question is calculate the energy production QR and the maximum energy production rate in rods. First part is at the axis, meaning the R is 0, and the second part is 20 inch away from axis. So the first part is we extract out information. Here is given that a 193 fuel assembly consists of 204 uranium oxide fuel. So the number of the N, the total rods is 193 times with 204. So we get 39372 rods total together. So the first part is calculate the energy QR. QR at axis 0. The R is 0. The formula is 2.32 times the power times energy deposited divided by n number of rods times the energy released. So compute in 2.32 times power is 1893 watt megawatt thermal times energy deposited, we assume 180, and 39372 number of rod time energy release. Energy release is normally 200. So we get 0.100 megawatt. So to convert into BTU, 1 megawatt equal to 34121 41 BTU unit. So by converting this, we get the final answer is 3.4. Here the answer is 3.43. Sorry, 3.34. 3.43 times power of 5 BTU per hour. So we write down first here because we will use the next step. 43 times 10 power of 5 BTU per hour. So this is the QR. So next step is to calculate the Qmax at axis. Qmax at axis is by using this formula. Q max is equal to 1 over 2 times h times a square times qr at axis. So compute in 3.43 times 5 over 2 times h is, the h is 144, but we want in feet, so divided by 12, 144 inch times the radius, the diameter is 0.42, so radius is 0.21, also divided by 12 square. So the final answer is 6 times 10⁷ BTU per hour feet cubic. So this is the Qmax at axis. So the next part is write down first. 6 BTU per hour feet. So the B part is 20 inch away from the axis. So to obtain a similar result for rod located at R 20 inch away, we need to multiply the previous answer, which this answer, by the factor appearing in this equation. Which equation? This is equation. So Q max is equal to Q max is equal to Q max J 2.405 times R over R extrapolated length. And also QR J 2.405 R over R. So So just times this factor here. So J equal 2.405 times R is radius the R position meaning 20 inch away, and R extrapolated is 67. We get J 0.718. Is also equal to in here so J 1.45 times 20 position R times the extrapolation, we get 0.875. so this 0.875 is the factor, so just times the previous answer to get the QR 20 inch is equal to this this previous answer is 3.43 times 10 power 5 times 0.875. We get 3.0 times 10 5 BTU per hour. So for the next part is the Q max 20 each away is the same. The previous one 4.66 times 10 power of 7 times 0.875. So the final answer will be 4.08 then power of 5 BTU per hour feet cubic. So that's all for the first question. The second question we go to here. So for the second question is derivation question. So derive the equation for total heat generated, which is capital Q T in an unreflected homogeneous reactor core of spherical shape and radius R. Neglect extrapolation length, which is R equal to RE. So this is the formula for unreflected homogeneous reactor core. Q the volumetric thermal heat strength is GF, meaning the energy times the density of fuel times the microscopic times flux times sine kurungan pi R. R here is the distance over R radius of the core, and divided by pi r distance over radius of the core. So in a spherical shell, the heat generated in the shell is equal to QR is equal to Q, the thermal source strength, the volumetric thermal source strength, times the area of the core, 4 pi r square, and this is the thickness of the thickness. So this is the diagram of a spherical shell. Here is the distance r, and r here is the thickness of the fuel, and r capital here, r capital is the radius of the core, and re the extrapolated radius length. So we have already assumed that r is equal to re. So it also given the question also given the GF is 190 MeV per fission, and also the converting factor is 1.5477 times 10 negative 8. To convert MeV per second centimeter cubic to BTU hour per hour feet cubic. So compute in all the formula here. QR to GF, G here is 190, also times this, straight away convert 8, GF and F not given, flux not given, this also not given, sine pi r over r, pi r over r times with this 4 pi r square times r thickness. So susun dulu, kita dapat Q R equals to darab ni 4 1.175 darab 10 negatif 5, and FF ni tak ada apa dulu, biar dulu. Flux R buat depan, sin pi, ni sin pi r, pi r over r, because ni dah padam, pi r over r ni potong, pi r over r, and thickness. Bukan, sorry, this one padam, and R here naik atas, R here, yes. So start integrate Q 1.175 times 5 and F by F R flux. So R0 R sine pi R over R GR. So down balik. Dapat 1 point. Ini atas dulu. R over pi sine pi R over R minus R over pi R cos pi R salin balik R0. So ni kosong, so R ni kena masukkan dalam R. Dan bila dah masukkan, dapatlah masukkan R sin R over pi square still sin masuk pi R potong sin pi minus R square pi cos and cos pi. So ini darab dengan ini final answer 3.75 darab 10 negatif 6 and FF R cubic flux. So that's all.